Uh, Hello. This video is regarding my final project for a Cpsc 5260 class. In this project, is I have implemented a random forest machine learning algorithm using MPI, and this is the title of the project is Application of Parallel Computing in Machine Learning. Let me briefly provide the introduction. Machine learning has become indispensable in solving complex problems across industries. Among various algorithms, random forest stands out due to its ability to handle nonlinear data, preventing overfitting and make robust predictions. Random forest is an ensemble method that trains multiple decision trees and combines their output for final prediction, making it versatile for both regression and classification uh, tasks. Random forest is basically of type supervised learning. Despite its strength, random forest training process can be computationally expensive, especially when dealing with large data sets or building high number of decision trees. This report presents a detailed implementation of our distributed random forest algorithm using OpenMPI. It incorporates enhancements such as double precision arithmetics instead of floating point arithmetic for numerical stability, and also use globally unique identifiers for trees. With passing interface MPI, the program distributes the computational workload of training multiple decision trees across multiple processes. This parallelization significantly reduced the time required to process large data set, making the program suitable for high performance computing environments. Motivation. Parallel computing offers a solution to the challenge of basically computationally demanding programs, as you can if you run those programs on the regular computers, you either not able to run them, or it takes a lot of time to run these computationally intensive programs. OpenMPI, a popular parallel computing network framework of a powerful computing framework, provides the tool needed to implement a distributed random forest algorithm efficiently. There are certain challenges. The first one is the high computational cost. Building and aggregating multiple decision trees require significant computational resources. Scalability. A single-threaded implementation struggle with large dataset and complex models. Numerical stability. Floating point calculation can lead to errors such as NaN values, compromising accuracy, and the solution to that is use a double floating point variables. Unique identification of trees. These ensure that distinct identifiers for trees in the parallel environment are there, and they are also critical for the program, as the identifier for the each tree should be unique. Opportunities. Parallelizing random forest training offers several opportunities. Efficiency. Distributing workload reduces training time significantly. Scalability. OpenMPI enables algorithm to handle large data sets and models. Flexibility. The implementation can be extended to GPU-based acceleration or hybrid parallelism. Real-world impact. Random forest training can improve decision-making in critical fields like healthcare and finance, and also technologies. Methodologies. The implementation of MPA rainforest algorithm involves following steps. Number one is the dataset design. The dataset consists of 1,000 samples, each with a numerical features, with four numerical features and one label. The label is calculated using the feature 1 and feature 2, and the formula for the label is feature 1 times zero point 0.5 plus feature 2 point 2 plus 3. This deterministic relationship ensures predictable outcomes, enabling validation of algorithm accuracy. MPI initialization. This is a very important step for before you can use any of the MPI functions like MPI scatter, MPI broadcast, or MPI reduce. The program initializes MPI environment using the MPI init. The root process, which is usually has rank of 0, reads the data set and broadcasts its size to all the processes. Unique tree ID, we have like used a formula to assign unique ID to each of the tree, and that formula is a tree ID equals rank start tree per process plus local counter. This guarantees that tree IDs are distinct across processes, simplifying logs and resulting aggregation. Other important process, other important functionalities is the tree training and functionality. Each process trains subset of decision tree independently. The training process involves recursive partitioning of dataset, selecting feature thresholds to minimize error at each split. Stopping conditions include reaching the maximum depth, which are using as 5, or having subset that cannot be split further. For instance, basically like a node that does not have any of the childs. Leaf nodes store the mean of the subsets label as a predicted value. How to We also use parallel prediction. After training, each process predicts output of all samples using its trees. The prediction from all processes are aggregated using MPI reduce, which computes the final result by averaging the outputs from all the trees. Implementation details. The key functions that I have written using the C language and the MPI functionality are a build tree. This function is a core. First one is a build tree. This function is a core of decision tree in training process in the random forest algorithm. It recursively partitions the dataset based on selected features and threshold to minimize error in the resulting splits. This function begins by checking the termination conditions such as reaching the maximum depth of 5 or encountering a subset of data that cannot be further splitted. This ensures diversity across trees in the ensemble. The resulting tree is represented as a binary structure of tree node objects, where each node stores the splitting criterion and the pointers to the child nodes. The function is designed to balance computation efficiency with model accuracy, making it a critical component of the random forest computation. The second function is calculated mean. This function is used in the tree training decision process for the regression task. It computes the mean of the labels within the specified subset of dataset, which is used as the predictor value for leaf nodes. The simplicity and efficiency of calculate mean makes it a foundational operation within the tree building process, as it determines the predictive value of at a terminal nodes. Additionally, the function bundle handles edge cases gracefully, returning zero when the subset is empty. And the third function is a predictory. This function is pivotal for utilizing a trained decision tree to make predictions on a new data sample. It traverses the binary structure of the tree, beginning at the root node and following the child node based on the input features of the sample. At each node, the function compares the feature value of the sample against the node's threshold. If the feature value is less than threshold, it moves to the left child, otherwise it proceeds to the right child. The predictory function is efficient and is designed to handle trees of varying depth, ensuring faster predictions. The fourth is a read data set. This function basically loads the data set from the CSV file into the memory. This function reads each row of the file extracting feature value and corresponding labels, and stores them in an array of data row structures. Now, MPI constructs, I've used MPI scatter, MPI reduce, and MPI broadcast. These functionality helps in determining the global predictions from the values of the local prediction. And we have divided the data into number of rows per number of rows for each of the per process. So each number of rows per process are handled by the MPI by the MPI reduce and basically combine to give the global prediction values. Results and performance. The implementation demonstrates significant performance improvement compared to single-threaded models, and the efficiency of distributed computing is reducing time while maintaining accuracy. Here are some of my observations. The first table has got the number of processes against the training time, and the second table has got number of processes against the training time, and the speed up was calculated by dividing the training time for one process to the rating time of the process, such as 2, 4, 8, 6, 16, 32. And here is the graph displaying the speed up and the training times. The results demonstrate the significant advantage of leveraging MPA for distributed computation in machine learning tasks. For example, experiments on a dataset with 100,000 samples showed that the training time decreased from 0.66 seconds with a single process to approximately zero 0.05 seconds with two process, zero point 0.08 seconds with four process and eight process, and 0.12 with 16 process, and 0.15 with 32 process. These results are shown in table 1. As per table 2, the speed up increased from 1 to 13.20. These results highlight the program's scalability as a workload is efficiently distributed among processes using MPA functions like MPA scatter and MPA reduce. This is the program output. I've taken a snippet of it and put it in the report for just the sake of basically if you are looking at it, you can have an idea what is the format of the program output. Data set snippet is the snippet of the data set that I'm using, and the code is a snippet of the C code that I've implemented for random forest algorithm using the MPI. A conclusion: the MPI-based random forest implementation demonstrates the power of distributed computing in is accelerating machine learning algorithm by leveraging for parallel training and prediction. By leveraging MPI for parallel training and prediction, the program achieves scalability and efficiency while maintaining accuracy and robustness. Future enhancements that I would recommend include implementing dynamic load balancing to handle uneven workloads, integrating GPU acceleration for hybrid parallelism, and adapting the implementation for classification tasks. Well, this is the end of my video. Thank you for watching it. Goodbye.